Hello guys and welcome back to my channel Civil Construction and Tutor, and in this video we will be modeling and analyzing a steel structure for residential purpose. So basically this is the architecture drawing that we will be using for the modeling, and it is a 2.5 story building. So ground floor, first floor, and this is the top floor plan. So let's start. Let's open ETABS. Let's go to file. Here we have new model. I have already uploaded a video for RCC design and I have explained all these steps. So the main focus will be with the steel structure analysis rather than all the other things like modeling and explaining the material definition, material properties, etc. So I'll directly go to the modeling and I'll explain the major part related to the steel structures only. So here we have using built-in setting, and display units will be metric SI, and here is steel design code IS 800 2007 and concrete design code IS 456 2000. So basically we are mostly interested with this steel design code. Okay, now for the grid formation we have 1 2 3 4 along x-axis, and similarly along y-axis we have 1 2 3 4, but the spacing is different. 12 11 12 feet 6 inch. So here we have option uniform grid spacing, so that doesn't work for us. So we'll just use the numbers only, that is the grid number. So along x direction it is 4 and along y direction it is also 4. Spacing we'll define this later on. Now number of stories, as I said, 2.5, that means 3. Similarly typical story height, so generally it is provided as 10 feet, so we can simply provide 10 feet. Okay, so you will see 2 windows. Now let me close one of this and let us close this model explorer as well. Firstly change the grid dimension. Right click over here and here you have add or modify grids, and go to modify grid system, and the first thing we have to consider is the displaying the grid data. So either we have display grid data as ordinates and display grid data as spacing. So in AutoCAD drawing generally we have the spacing between grids, that is grid spacing only. So we'll select this option, display grid data as spacing and number of grids. So when we are considering the spacing, the last spacing value should be 0, and for ordinate it will be the first value. So grid spacing, now let us see the AutoCAD drawing. The first is 12 feet 11 feet and 12 feet 6 inch. So you can simply write 12 and give the symbol of feet, it will automatically convert this into meter. And the next one is 11 feet and final one is 12 feet 6 inches. So like you can write this. And similarly along y-axis we have 11 feet 10 inches and 12 feet. So 11 10 and 12, 11 feet 10 feet 12 feet. Okay, so the grid formation is done. There is no need to change for the story as it is same. So for now, okay, let's start with the 3D view. So grid formation is done, and now we'll start with the material properties. So we have by default some materials. We will not use this, we will define our new one. So add new material, and here you will select India, and we have concrete material type and steel. So first we will define steel, Indian, and grade generally we will use Fe 250, that is mild steel. Okay, no need to change here. Then okay, similarly add new material, we have to define concrete slab as well. So simply select India again, material type will be concrete, and M20 shall be sufficient for the deck slab. Okay, no need to change anything over here again. Now let us define the rebar material for that slab as well. So here we have rebar and it will be HYSD 500 grade. Okay, so this grade steel has been done, concrete has been done, and rebar material has been done. Okay, now let us go to the section properties. We have to define the frame section, beam sections, and then we have slab sections. It is a steel structure, so it might require secondary beam, and to support the deck slab we will require stinger beam. So let me show you in real site images. So before that let us see in the ETABS model as well. So this is how the structure will look, the structure that we are going to model. So basically, let us turn the extruded view. Okay, so these are the column posts. This can be either I-beam, it can be a square pipe, or it can be a built-up section. So built-up section basically means a section made up of two individual steel sections. For example, here you can see it is made up of two channel sections. And are connected with the batten plates. So this is a column section. Similarly, these are the I-beam, that means these are the main beams in the structures. And as I said, this is the deck slab and it is supported by Stinger's beam. Stinger's beam and secondary beam, these are two different things. And obviously we have already made a video on the truss section. So this is the purlin, these are the raptors, these are the vertical cords, and these are the inclined cords, or also known as struts. This is the central post, and as I said, this is the purlin that runs throughout the structure, and it is the main load carrying, or the load from the CGI sheet is transferred to this in one-way direction. Now let us see in the real field as well. So this is one of the steel structures being built, and you can see the members. So these are the column post, these are this beam, and these are the Stinger's beam. This is the built up column connected with the batten plates. This is the deck slab sheet. So this is the deck sheet, generally of 0.8 mm to 1.4 mm thick, and these are the Stinger's beam. This is the main beam. Here you can see these are the ribs. So ribs are going in this direction, and the Stinger's beam follows a perpendicular direction to the rib. So this is the typical column connection, column and beam connection, with provided with this stiffness and bolt. As you can see, this is the deck slab and there is a reinforcement provided. These are the temperature reinforcement, and the column is rested on a column pedestal supported on a base plate. So I'll discuss that later on. So I think you can now visualize the element of the structures, steel structures. So now let us go back to the modeling. So we have defined the material. Now let us define the sections. So first we will define some frame sections. Okay, let me delete this first. So these two will be deleted later on. So now for defining, either you can just define on your own, or you can import by default properties or by default sections. So let us go to import new properties, and here you have options for the steel I, channel section, box section, or pipe sections. So let us go to I section. So let us first define beam sections. So it will be in Indian, and here it will be FE 250, and you can see here ISHB, ISMB, ISLB. So L means light, M means medium, and H means heavy. So in general purpose, we should also consider the commercially available sections. We cannot just go for any sections and design. So for now, let us select ISMB 150, 125, 200 and 250. Okay. Similarly, let us import channel section. So for this we will select medium section, and ISMC 200, ISMC 150, ISMC, okay, this should be sufficient. Okay. Similarly for truss, either you can use box sections or tube sections, so we'll import both. And for box section, the Stinger beam are provided like in form of box section. So IS 6633 into 3.6, this is one of the commercially used Stinger beam. You can also go for IS 72 by 72, and you can also go for 96 by 48 into 4. Okay. Similarly, let's import some pipe sections. So commercially used are ISNB 32M, 50M, 65M and 90M, or also you can go for 100M. So for purlin we may require 90M or 100M. For raptors we may use 65M or 50M, and cords, that is vertical struts and inclined struts, can be used with or can be passed even with 32M. and this is for residential purpose, and it may not be always true. These are just initial guesses for the section that I am going to use. Okay, so frame properties has been done. Okay, now okay, let me delete the other two. So ISLB 600 and ISWB was not our guess. Okay, so section properties. Now let us define slab sections. We'll define both, that is slab section as well as deck section, and we'll check the results. So firstly let's define slab. So I'll modify this one. So slab 75. So basically the dimensions. So this is the general standard drawing of the deck slab. These are the column, these are the beam, and this is the secondary beam, and the slab is resting on the stinger's beam as well. And if we see the typical section, so it should be something like this. So these are the rib, and we have the slab thickness as 62 mm and the rib depth as 63. That means overall 125 mm, that means 5 inch thick, and it is resting on 0.8 mm decking sheet. The bottom dimension of the rib is 106. Similarly, you can see that the top width of the rib is 144, and the central to simply we can say center to center spacing of the rib is 250. So this is a general standard. We provide nominal reinforcement, and these are the studs, 12 mm bar as vertical studs to connect the rebar and metal sheet, and they are connected with each other with the tack weld provided over here. And as I said, the stinger's beam are provided perpendicular to the direction of the rib. So these are the stinger's beam. It may be a I beam or simply a tube section, and this is the rib direction. So they are provided perpendicular to each other. Now let us define it. So firstly let us define the deck sections over here and just modify this. So deck 125, and we have type as filled, unfilled and solid slab. And to understand, you can simply place the cursor over I, and you can see this is the filled deck, this is the unfilled one, and finally we have solid slab here, and all of these have modeling type as membrane. So the basic difference between this membrane type and shell is that the membrane does not possess any bending stiffness. That means it is a simple type of bed sheet, which is not true in the case of a concrete slab of 5 inch thick. So if we model a deck slab only, then we are just applying the load of deck. It doesn't provide any bending stiffness resistance, which is not true. So we have two options: either we can model this and provide greater size of a stinger's beam, or we can simply model a slab, shell type slab, and design according to it. So we'll do both. So we'll select the filled one, and here we have M20 grade of slab, and the deck material is Fe250, that is the deck sheet, which is 0.8 mm. And now let us override this. So slab depth, basically the clear slab depth we have here is of 62 mm, or we can simply say 62.5. so 62 mm. Rib depth is 63 mm, so this comprises to a total slab depth of 125. Rib with top, so this is 144 mm top width, 144. Bottom width is 106. Rib spacing, center to center rib spacing, it is 250. Deck shear thickness, so it is, or it ranges from 0.8 to 1.4, so 0.8 mm. Deck unit weight 0.11 kilonewton per meter square. Shear stud diameter, so as I said, the shear stud over here, so these are the shear stud, and these are provided to connect the rebar and the metal sheet. So 12 mm, so 0.8, and this is 12 mm shear stud diameter. Shear stud height, so it is provided almost equal to rib depth, so that means 63 mm. And shear stud, this is 12 and this is 63, and this is 410 for the Fe250 tensile strength Fu. Okay, I'll also define a slab sections. So let us modify this, and this will be simply slab of 75, as we have a slab depth of 62 mm and a rib depth of 63. So averaging these two will get a average slab depth as 75, or simply 3 inch thick, and this will be M20 and this will be 75 mm. Okay. So we have defined the sections. Now let us define the load patterns. So here you can go to load case patterns, and so we have dead load and live load by default. Let us add the wall load, and it will be a dead type, and self weight multiplier will be 0 if we are not going to model that and applying the load manually. So add new load. Similarly, we have floor finish FF, so that will be also dead and it will be self weight multiplier 0. Then we have EQX, being a steel structure but provided with the deck slab, the self weight or the seismic weight becomes more, and hence earthquake load becomes more dominant than that of the wind load. But we'll apply the wind load to the truss, so it will be a seismic. And let us select IS 1893 2002 and add new load EQY, and this will also be the same. And we have wind load, that will be wind, and it will be none. We'll apply it manually, and if you are going to use the IS code, you can simply select the IS. So for now it is none, and add new load. So self weight multiplier 0. Okay. So now let us define the earthquake load. So go to modify lateral load, and for X let us uncheck all Y, and the story range will be from base to story 3. Response reduction factor 5 for steel structure, that is MRF. So you can find that in our earthquake code. So response reduction factor R. For moment frame system with steel buildings with special moment resisting frame, it will be 5. So 5. And seismic zone factor for zone 5, it is 0.36. Site type 2, and importance factor, as it is a residential building, so keeping this as 1. And time period, either you can go for approximate, program calculated, or user defined. So the difference is between the time period factors, that is the approximate CT value. So if you see in the code, for RC building it was 0.075 times H075, and for steel MRF building it is 0.085. That means the time period is greater for steel building considering its ductility. So it will be 0.085, or you can simply go as 0.085 times height of building, which is 9.16 to the power 0.75, or simply go approximate. Select this, we'll paste for EQY as well. Okay. Modify lateral load, so uncheck X direction and put this as user defined, and time period will be this. So okay. Now let us define the load combination. Add default design combos, and we simply have this as steel frame design. Convert to user combination editable. Okay, define, and here we have mass source as well, because we are considering earthquake load. So mass source, modify, untick this element self mass and specified load patterns, and add this. Then we have live, this also once multiplier, but for live greater than 3 kilonewton per meter square, the multiplier will be 0.5, and for load less than 3 it will be 0.25. so generally the live load for the residential building is less than 3 kilonewton per meter square, so we can simply write 0.25 over here. Then we have wall load, and the multiplier will be 1 because it is a dead load, and we have floor finish, it is also 1. So these are the mass source. We will not consider EQX, EQI or wind load for this. So as I have shown here, you can see a built up column, and in some cases we might see a simple I-beam. That depends upon the load type. If it is sufficient, then we can simply provide a I-beam, or in general practice we will provide a built up section. Let us define that as well, and for that let me close this now. Simply go to define. Here you have section properties, and here we have frame sections, and go to add new properties, and here we have section designer. Go to this, and So before modeling a section, that is built up section, we have to understand the connection requirement as well, that is the beam and column connection. So I have prepared a 3D model here. You can see this is a typical built up section, and this is how the beam will be connected to the column, and that means the width of the flange will govern the this dimension of the column, because it has to be connected on the batten. So there should be sufficient freeboard to ensure proper connection of weld, or even if it is bolted connection. So basically we are going to use channel sections initially. This being the channel section, we have two type of connection. One is face to face and another is back to back. At this region we have to provide batten plate as well. For example, this is the batten plate connection, and it will be welded in this particular point. So we'll provide a clear gap as well at this face. So generally for the residential building, the section for beam may be used as ISMB 200, 250, 150 depending upon the condition, but it is not provided greater than 250. Generally we may go up to 300 as well. So for now, considering 250 as the maximum size, that means the beam is going to rest and be connected on this point, on this face. And if we see in the plan, so this will be the flange of the I beam that will come, and this is the wave. And we have to consider the flange width, and as we are going to provide connection over here, so that has to be considered. Now considering this as ISMB 250, we get the flange width BF as 125 mm. So that means this section should be greater than 125 mm minimum. So we could opt for ISMC 150 for this face. Now considering this face, we are going to provide batten, and we are also going to provide I beam that will rest on this face. So this is 125. We are also providing batten, that means extra length is required. So if we are providing bolted connection, then we have to provide end distance as well. So considering these all parameters, ISMC 150 will not be sufficient. We have to go for a bigger sections. Now let's see in the 3D as well. So this being a typical connection, for this I have prepared an Excel sheet. So you can see here, either you can have face front to front or back to back. So this is the front to front, or you can have back to back. And the equation that governs these two are this. And as I said, spacing will be provided in such a way that moment of inertia of the section about the both axes becomes same. So we have two sections, so 2 times of Ixx is equal to 2 times of Iyy plus A dy2 plus Cyy. So the major difference between these two equations is the sign. So for face to face it is minus, and for back to back it is plus. Ixx, so this is moment of inertia along x-axis, moment of inertia along y-axis, A being the cross-sectional area, D being the spacing, so this is basically D, and Cyy being center of gravity. So let me consider 150. So ISMC 150. So for this, area will be sectional area 20.88, and this is effective area, that means twice of A. This is for one channel section. So for two channel sections it will be 41.76. H, which is the depth of the section, so for 150 it will be 150. Flange width, it is BF, so you can see here it is 75 mm. Cyy, it is 2.22. Rxx being radii of gyration 6.11, and for YY it is RYY, it is 2.21. Moment of inertia IXX 779.4, and along Y it is 102.3. TF being thickness of flange, which is 9, and thickness of wave is 5.4. And the section we have selected is ISMC 150. So for this, using this equation, considering face to face, the spacing of C sections come as 158.29. This is D from the outer face. So adopting 160 as the spacing, and this being 150 mm for ISMC. Now if we provide 125 mm flange, considering ISMB 250, will it be sufficient or not? That is the question. 125 is the flange width, and if we provide clear distance on either side for both, considering the weld size, so it comes as 120, that is the batten size, and the flange width is 125, which will not be okay. So ISMC 150 is not suitable for this type of connection, so we'll go for a greater sections. Let us go for ISMC 200 and we'll check. So now let us substitute the value of ISMC 200. So this is 28.21, so into 2 it is 56.42. For 200 it will be H will be 200. Flange width for ISMC 150, 175, 200 is same. So what is the point of shifting to 200 then? It is all about area and moment of inertia, so it will change the parameters. Okay, CYY it is also 2.17, not great difference. RXX, this is 8.03. RYY it is 2.23. Now if you see IXX, there is a vast difference, 779 and 1819. So 1819.3 and 140.4, 11.4, and this is 6.1. Now let us see, considering this equation, the spacing now comes to be 197.69. so I have used this equation. You can simply calculate this value D by substituting all the parameters. Now the center to center spacing of the C sections is 200, and considering the gap of 20 mm on either side, we get the batten size as 160 mm, and the flange width is 125 only for 250 mm beam. So there is sufficient gap, so this section shall be suitable for the connection purpose as well. So we will design for ISMC 200. So then let's rename this as 2ISMC. The material Fe250, general steel section. We have section designer, and here we have to draw the sections. For that we'll require the details, and I have already summed up the steel dimension and properties for ISMC 200. So go to draw, here you have steel and go for channel and click over here, and you will simply get a channel section, but the dimensions are not as per our requirement. So select this all, or just click over here and right click on this, you will get the section properties. Now we can define as per our requirement. So height, obviously it is ISMC 200, so 200. Flange width, so we have to see, so flange width is 75. Flange thickness 11.4. the web thickness was 6.1. Okay, now we have to provide certain offset along x direction. Along y direction we don't have any offset, but along x direction we have certain offset, so we'll provide that as well. So you can see here the spacing came to be as 200 mm. So if we provide here as the origin 100 mm to the left, 100 mm to the right, that will be sufficient. So simply saying this coordinate should be -100, but it is -37.5. So right click on this and along x-axis 37.5 minus 100, so minus 62.5, and we'll get this. So if we put here, we'll get x as -100. Now the same thing shall be replicated at this face. So select this and go to edit, replicate, and here go to mirror and select y-axis. Okay, so you will get the replicate section. So it is 100. So the overall length along this direction it is 200, and at this direction also 200. This is simply a built-up section, but we also have to provide batten. We'll provide that later on basis of the axial load. So for now, just we'll define the built-up section without batten. Now, okay. No need to modify any property modifiers, because for steel section we'll consider the gross moment of inertia. This is as per IS code as well as NBC 105 2020. Okay, so built up column is also done. Now let us model the structure. So this is the story 1, and for this we have this architecture drawing. So we have column on all grids, but it is different at the top floor, that is we don't have columns for this. So let's start. Simply select quick draw columns and here select 2ISMC 200. Let us draw it. For now the orientation is along this direction, and in certain case if you want to provide this along the y direction, then you can simply select and go to assign frame local axis and provide a rotation of 90 degree, then you will simply get along y axis. For now let us provide along this direction. So assign fixity at base. So simply we have modeled the column. Now let us model the beam for the first floor level. Go to quick draw beam and here we will select let us start with 200 and we will provide for all the grid intersections. So this is how it was supposed to be modeled. Now let us replicate for this floor as well. Go to plan story 1 and select this all and go to replicate, Ctrl R, and story, select story 2 and 3, apply, and go to the top story, that is 9.144, and we will delete this as per the architecture drawing. So this is open space, so only this will be modeled. Let us delete this and go to the 3D view, turn on the extruded view, and let us select DirectX. So this is how our steel structure will look. So you can clearly see this is a built up column. I beam, as you can see, it lies within the flange, so there is no any issue regarding that. Or you can, for a darker option, select standard graphics and you can clearly visualize that. So modeling is done. Now let us apply the load. Go to plan story 1 and we'll apply the load. on extruded view, and let us apply the load according to the architectural drawing. So we will not consider this because we are not going to model the plinth beam. We'll directly design this one only. So this will be the plinth beam. Nominal plinth beam will be sufficient. We'll check that later on as well. For now, let us go to this first floor plan. So this is where this wall will rest. So we'll apply the load on these beams. So these face do not have any opening, and these face have opening. So they are external walls. So let us consider external wall of 9 inch thick. So we'll assign the load. So frame load distributed. So firstly we'll provide to the section without any openings. So select wall. So we are providing a uniform load, UDL. So 9 inch thick means 230 mm, and height basically 3.04. It is the total height of the floor excluding the beam depth. So we get ISMB 200, so 0.2. So this is the total height of the wall. So multiplying it with 19, that is the unit weight of brick masonry, into thickness of wall 0.23. So this is 19 kilonewton per meter cube, and this is meter. So we get in terms of kilonewton per meter. So this comes as 12.44. Now apply this. While this face being external walls but are provided with openings, so let's assume 25% of opening. That means only 75% of load will be applied. Apply. So this is the external wall loading for the first floor, and there are partition wall inside which are resting directly on the beam. So let us select those beams as well. Okay, so these three do not have any load on it, so we'll select that. 3.048 minus 0.2 ISMB 200, 19 into 0.13, considering a single brick wall. These are a single brick wall, so thickness will be 0.13 only. So it comes at 7.035. We will not consider this opening for now. We'll just directly apply whole load. So this is the loading of wall for the first floor. Now let us go to the next floor. So for this we'll apply the load. So these are full wall load without opening. So it was 12.446. So 12.446. So 1, 2, 3, 4, 5. These have certain openings. So we'll consider only 75%. And there are partition wall which have 7.035 as the wall loading. We also have parapet wall on these beams. So select this. Considering 1 meter high parapet of thickness 0.13, we get 2.47 load. So simply apply 2.5 kilonewton per meter as the parapet wall load. So this is about the wall load. Now let us model the slab and we'll apply the floor finish and live load on it. So select quick draw floor or wall. So firstly we'll model slab and then we'll check for the deck as well. So select the grid. This is the opening for a staircase. And for the top floor, we will provide truss. Now let us model the stinger's beam. And stinger's beam are provided perpendicular to the ribs. So let us assume the ribs are provided in this direction. So the stinger's beam will be provided in this direction. And for this, simply go to quick draw. And here you have property. And let us start with ISB 6633. Moment release as continuous. Number of beams. So let us take 4 numbers of beam, and this should be placed parallel to y to r, and for according to this, so y to r, and if the direction is in this way, you can simply place parallel to xt, so parallel to y. Go to the upper floor. So stinger's beam are also done. Now let us apply the shell load. So before that, let me hide the stinger's beam. Hide selected objects, or you can simply select all this and go to assign. We'll assign the shell load, and here we have uniform. So even if it is selected for frame, it doesn't apply the load on the frame. So apply live load of 2 kN per meter square and a floor finish for 1.5 kN per meter square considering marble finishing. Apply. Okay. Either we can model staircase, or we can simply apply the dead load of it on the beam on which the stair is supposed to rest. So the beam is this on which the staircase will rest. One of this it is, and a single flight will rest on this beam. So for that, let us define the load pattern. Stair dead, or simply we'll apply the stair load. Add new load. Okay. I have already uploaded a video regarding the calculation of the dead load of the stair. So for now, I'm just going to apply a load value on it without calculating it. You can simply find that. I'll take an approximate load for the stair. So for now, let us assume the dead load for this type of dogleg staircase as 22 kN per meter for 2 flights. That is, 2 flights are going to rest on this. Okay, so if it is start from here, and one of the flight will rest on this, and the another will start from this, and for mid landing, the load will be transferred to this beam through the wall provided over here, and this will give load of 2 flights, that is 22 kN meter, and from here a single flight will rest on this, and there won't be another flight starting from this beam. So select this 2 and we'll assign frame load of stair, and this will be 22. Similarly for this, but will be provided up to its midpoint, so the flight will rest at this half. So for applying the load for the half portion only, we will be using this trapezoidal loads, and for that we have to know the I point and J point. So I means the starting point, as we are using the relative distance from end I. So right click on this. Here you have end I and end J. We can find this from the coordinate. So along y axis, so right click on this, end J and end I. So coordinate 3.35, 6.4. So this is end I and this is end J. So we'll consider from end J, that means 0.1. So 0.5 half, and this is the other half portion, 0.5 to 1. So this will be 22, this will be 22, and this will be 0. Apply. So this is how the staircase load looks like. Now let us model the truss. So for that, let us go to the elevation view 1. I'll provide a point above the midpoint of the beam. So select here, you can snap option and select all. So make sure that line ends and midpoints are ticked. Apply. Okay. And for maintaining slope greater than 12 degree, so the length of this beam is 3.65. so if I provide a rise of 1 meter, 12 degree inclination will be achieved, and for draining of the rainwater, 12 degree slope is minimum. So go to draw joint objects in z direction 1000 mm. Similarly, I will provide certain offset on either side, so it will be easy to make the connection. Let me provide 300 mm offset, minus 300 mm in this direction. Simply select this and extend up to these 2 points. Now let us model the raptors. So for raptor, I will be taking ISNB 50M. So this is the bottom raptor. You can simply assign this as well with ISNB 50M. For now it is ISMB 200. So let me divide this into 2 equal half first. So let me divide into 3 equal halves now. ISNB 32M. So there may be a chance of failure if I don't connect on the post. So I'll simply provide like this. So there is less chance of failure, and I will join this frame. So truss has been modeled. Now we will replicate this along this direction at these points 1, 2, 3, and before that let us delete this beam because we will replicate this. Now let us select this truss member and we'll replicate them. So for this simply press Ctrl R and you will see this. Using linear option, we'll pick 2 points and replicate them. So from this to apply, get. So you have previous selection. So selected. Now pick 2 points from here to here. So now we have to draw the purlin as well. So the purlin will rest on these points. So we'll select this point and we'll extrude them into frame. So the purlin will run from this point to this point. So we'll extrude them to a length of this value. So simply go to edit, extrude joints to frame, pick 2 points and we'll assign up to this point. Put this as 1, apply. So you can see purlin has been modeled, but we have to check the assigned section as well. Right click on this and you will see it is none. So we'll assign them with the proper section. Select all the purlins, assign frame section properties. For now let's select ISNB 65 MB, apply. I have already made a video regarding the calculation of load for the truss, either that is for CGI sheet or live load or even the wind load. You can check that video. I will just take the approximate load value depending upon the calculation that I have done previously. So it will make the video longer. Just check that video if you want to understand about the load that I have provided in this video. So I'll directly apply the load on the purlin. So we'll exclude the outermost purlin, because it will only carry the load from one CGI sheet, while other purlin will carry half load from here and half load from here. So let us select the interior purlin only and assign frame load. So for now let us apply the dead load of CGI sheet as 0.1 kilonewton per meter square. So depending upon the purlin spacing it will be computed, and spacing of purlin for now it is 0.7. so 0.1 into 0.78, so this comes as 0.078. so make sure that the load is applied on the purlin only. And for the outermost purlin, as it is carrying a single CGI sheet load, so half load will only be applied on it. Now again let us select the innermost purlin and apply the live load. So up to 10 degree it is 0.75. so if there is increase, for now it is 29 degree, so for that the live load will be different, so we have to apply according to it. So let us assume it to be as 0.65, and similarly we'll apply the wind load, and wind load will be applied along the local axis 2 for frame, and for area, that is cell, wind load is applied along direction local 3. So for now let us apply wind load of 1.2 kilonewton per meter along local 2. So we have to rotate the local axis according to the pitch of the roof. Okay, now let us apply on the outermost as well. So half of this will be 0.6, apply, and let us select half of the purlin from the ridge line will be tilted with positive angle, and half of the other purlin will be tilted with negative angle. So up to here this tree will assign frame local axis with the inclination. So for now it is 1 meter and the length is 3.6. so you can simply compute that as tan inverse 1 divided by 1.8. so with an angle of 29 degree minus 29, apply, and the other will be tilted by positive 29 degree. Now display frame load assign wind, and you can understand it now. So according to the pitch of the roof, and for central there won't be any inclination, and the outermost is to be provided with the live load as well. So assign gravity, so 0.65 means 0.325, apply. So finally load assignment is also done. Let us assign the diaphragm. So all objects and go to define. Here you can see diaphragm. So D1 is by default defined, so rigid, okay, cancel. Now so go to plan story 1 and select all the horizontal members, assign diaphragms and assign D1. Similarly for the second floor, assign D1. So it is not necessary to provide different diaphragm for each floor in ETABS. Just assign D1 for each floor separately, that will work for it. ETABS will directly assign a different diaphragm even the naming is same. So diaphragm assignment is also done. Now let us check the model. So model has been checked, no warning messages were generated. So now we are ready to run. Before that let us check the preferences. Viewer revise preferences, and here all the values are default value, And the major thing we have to consider here, demand capacity ratio limit. So if the value of demand capacity is greater than 0.95, it will show red color, and that means to the failure value. And design code IS 800 2007. Okay, framing type SMF, that is for the ductility consideration. Okay, you should also check the design combination, so which was our default design combination for steel frame design. So let us run the analysis. Let us save this. Okay, now let us run the steel frame design. So go to this and verify all member passed. So one steel frame has failed, so selected object. So one of the beam here is failing 1.049, not a greater value from 1, but still has to be optimized. Okay, so all. And the other thing is, it is failing in the compression, and if you if you check the details, ETABS will take the effective length ratio, which is 0.65 times of L for the both side restrained, but will take a value greater than 1 or equal to 1. So K factor for measure buckling mode, the basic factors is 1, which can be overwritten by 0.65 if it is failing in compression. But for now I will change the section. There are other members which are near to. Okay, let us see the design capacity ratio as well. So display design info, here you have PM ratio colors and values. Now it will show the value as well. So it is 0.961. So we'll change certain sections and see whether it is past the optimized section or not. And similarly, you can see at the top the column size or the PM ratio for the column is 0.2, which is very less than 1. So this can also be optimized. And this beam which we are provided as ISMB 200, this can also be optimized. So let's unlock this and go to plan story 1. Okay, before that let me check with the deck slab as well. So as we have assigned a sail thin, so if you see here slab section and this is a sail thin. So the basic difference between these two is that the sail can resist moment and shear, but the membrane, okay, let's see for the deck. It is membrane type, so membrane can't resist moment and shear. So for now, as I have modeled this as sail, so it will resist certain part of moment and shear, and hence the stinger's beam passes without any failure. For now, let us assign. Okay, firstly let us go to 3D and select all the slab sections and assign the sail as deck sections. Apply, okay, and run. So you can see the stinger's beam have failed now. The basic idea here is that 100% of the load transfer of the sail or the slab is directly to the supporting structural members. The sail doesn't possess any stiffness, doesn't possess any resistance for moment and shear. That is, we are just applying the load on the stinger's beam. That is not realistic. So modeling this as sail is much more realistic, as the sail or as the slab has certain stiffness, but modeling them as a deck, that is membrane, we are just being conservative and we are just making the supporting members much more safer. So if we are modeling this as deck slab, this will require a greater size of the supporting members, that is stinger's beam. We are at the safer side, but this is not realistic, it is just conservative. So the basic idea between slab membrane and slab, that is sail slab, is the difference of the load transfer mechanism. Membrane doesn't possess any stiffness, it will transfer all the load to the supporting members. So that means you are providing a greater size of the supporting members, you are in the safer side, but that is not realistic because you are providing a slab of 5 inch and with certain revers, it will obviously have certain stiffness. And if you are designing the slab, you cannot design considering that as a membrane. So you have to consider that with the cell type. So this is the difference between these two results. I hope you understood. Now let us optimize considering that as a slab. So let's unlock this and control J, that is get previous selection, and we'll assign it as slab section, and the purlin member failed at the top, so we'll provide that. Select properties, frame sections. So IS NB65 we had provided. Let us provide that as 190 m, that will be sufficient. And for the beam at top floor, we can simply change this from ISMB 200 to a square pipe, as it is not necessary. Assign frame section properties, and we can simply provide 72 by 72, and at the first floor the periphery beam can be provided with, okay, verify all member pass. So all member pass. So our modeling and analysis of the steel structure is done. Now let us check the model mass participation and similarly the story response plot. So for that, display, and here you have story response plot. Okay, firstly we'll check the mass participation. Okay, we'll also check the auto seismic load assigned, and here in the structure output you have model information, frequency and mass ratios. You can also check center of mass. Okay, so center of mass and rigidity. So you don't have the center of rigidity, and we have center of mass. So for this we have to check the center of rigidity as well. So I'll do that. And load, seismic load definition. So coefficient use 0.09, time period use this, and this is the seismic weight. And model mass participation ratios. So and at the nth mode the mass participation is 100%, that is greater than 90%, so it is okay. And similarly the first mode is translation along y, second mode is translation along x, and in third mode the building undergoes torsion, that is twisting motion, so that is also okay. And thirdly we have a model frequency. So for the nth mode, that is for the mode in which 90% mass participation occurs, the frequency shall not exceed 33 Hz. And for our case 90% mass participation occurs in the fifth mode for both axes. So at fifth mode the frequency shall not exceed 33, which is simply 4.5. This is also okay. Now let us check the story response plot and check the story displacement and story drift for EQX and EQY. So this is similar to that of the modeling of the RCC building that I have already uploaded. So EQX and story displacement is 18.71, and the maximum story displacement is to be taken as h by 250, that is height of building divided by 250, or simply 0.004 times of height of building. So let us compute that. 0.004 times of 9.16, so it is 0.036 meter. So converting this into mm, 36 mm is the maximum displacement, so it is simply 18.71, and along y direction 22, which is less than the permissible value. Similarly let us check story drift. Along EQY it is 0.0026, which is 0.004, that is maximum value is 0.004. Inter-story drift, you can find that in the code, and it is 0.002261, so it is also okay. Now we have to design the connection, we have to design the base plate, we have to design the pedestal and footing. So for designing the column to beam connection, we can simply use the load, that is shear force and moment, for the connection design over here. And for designing the footing, we'll use the reaction developed at the base, and we'll design the base plate and then pedestal and the footing. So that will be in the second part of this video. If this video gets proper response, I'll be uploading the video regarding the connection design, base plate design, as well as the pedestal design. So one thing we have to do here is the batten design. So simply unlock this model, go to the section properties, frame sections, we'll make a copy of this property. So this is without batten, and now we'll make this section with a batten. 2 ISMC 200 with batten. Section designer, draw steel, and we have plate over here. So click on any point. Now select this. Let us provide a plate of 8 mm thick and width. So this width is 200, and I calculated with 20 mm free at both ends. So this comes as 160 mm. And offset, so this is 100, so this will give 200. So the offset will be 100 along y direction. Okay, so it was for the midpoint, so we have to assign 104. If there is overlapping by a few mm also, then you can check for that. So check section for overlap. You can see plate 1 and channel 6 are partially overlapping, which is not correct. So it should not be overlapping. So for that we'll provide an offset of 104, and you can see there won't be any overlapping. And we'll also provide this in this face. So select this, edit, replicate. Now as we have provided offset along y, so it has to be mirror about x-axis. So we can see and check section for overlaps. So there is no overlapping. Okay, okay. Now add new property. Now we have non-prismatic. So we'll make a section made up of these two members, that is ISMC with batten and without batten. So the starting section will be with the batten, and we'll provide a length of 0.3. So I'll make a separate video for calculation of all these using the Excel sheet. So the second will be without any batten, and the length will be, so this is the end batten. So the end batten will have a greater dimension. So this is without batten. Let us assume this as 0.2. So the overall height will be 3.048 meter. So select this and paste, copy here. It will be 0.2, let us assume. So this will be 0.3. So again it will be without any batten, with batten. So these are the intermediate battens. So the length should not be greater than 3.048 meter. So let us compute this overall length. 0.3 plus 0.3 plus 0.2.3.2.3 plus 0.2 plus 0.3 plus 0.2, 0.3, 0.2, and okay, we can simply delete this and replace this with batten, as this will be the end batten. So simply delete this. 2 ISMC 200 built up. Okay, so now let us check the extruded view first without batten. So it is something like this. Now let us select, or we can just do like this, select the column and we'll assign with section properties as with built up, apply, and now let us see the extruded view. So you can see batten. So this is the end batten, these are the intermediate battens. So in this way the battening shall be done. So the battening is computed with respect to the axial load. So basically the batten is to be designed as it will take 2.5% of the axial load that is acting on the column. So on that basis the batten is designed, and its spacing, its weld thickness. So let us again run. Okay, so this is how the analysis of a steel structure is done. I hope this video helped you, and if it did help, do like and subscribe our channel, and make sure to comment the video that you want me to make.